So in previous class, we have seen pass 1 algorithm and pass 2 algorithm. So today, let us go to next program, which is written in SIC which is written for SIC So before that, we will see here what all the facilities are available in SIC Okay, see the program which was written in figure 1, that is the program for SIC. The same program is rewritten here in the figure 6 to take advantages or benefits of SIC instruction set. Okay, so here in our assembler language, indirect addressing is there, right? Indirect addressing, and I already told you how to identify that it is indirect addressing. This indirect addressing is indicated by adding or prefixed with the @ symbol to the operand. So before operand, if you get @, it means that it is in the indirect addressing. Similarly, if the operand is prefixed with the hash symbol, then it is called as immediate addressing. Okay. So here instructions which are usually use memory. Okay. So instructions which use memory. So usually they will be converted or they will be translated using either program counter relative addressing mode or base relative addressing mode. As from earlier from beginning I am telling you. So these two addressing modes are very important and most frequently used addressing modes. These are called as relative addressing modes, and why we should use these relative addressing modes, that is also I told you. So it is one solution to solve our problem. Our problem was 15-bit address field was not taking the complete address, and the complete address was unable to fit in a 15 address bit field. So because of that only, we had two solutions. Either we have to use a relative addressing mode, one among them, or else second solution was we should extend our 15-bit address field to 20 bits address field. Okay, so these are the solutions what we have find, and here is almost all instructions will be converted into machine level language by using any one of these two addressing modes, program counter relative or base relative addressing mode. And remember, our assembler, whatever we are studying now, so maximum number of times it gives a first priority to program counter relative addressing mode only. Okay, program counter relative addressing mode, if it is not possible to solve that instruction, if it is not possible to translate that instruction with the program counter relative addressing mode, then assembler starts to use a base relative addressing mode. The formula to find out the displacement is equal to target address minus the content of the register PC, or else the target address calculation, if you want to write, the formula will be like this: target address is equal to displacement plus program counter register, PC register. So here if you want displacement, then displacement becomes target address minus PC. Similarly, for base relative addressing mode, displacement is equal to target address minus the register B, okay, base register. So base register is used for addressing purpose. The assembler directive BASC, capital BASC, yesterday I told you in line number 13 of your program, you can get this base assembler directive. In addition to those 6 assembler directives, this is also one more assembler directive. Along with this one more base assembler directive is there, that is a no base. So this base assembler directive is used in a conjunction with the base relative addressing. It means it is always used with the base relative addressing. So if the displacements required for both program counter relative and base relative addressing are too large, So see here, very important points I am going to discuss today. So displacements, whatever we are going to calculate for both the program counter relative addressing mode or relative addressing mode, if the value of this displacement is too much large to fit into this 3 byte instruction, then the 4 byte extended format can be used. Okay, so it means that the when I was discussing about addressing modes of SIC XC machine, in bracket I had given there the range of the value of displacement. For program counter, it should be from some 0 to 2047 and something like that I had, I think, given. Okay, so if the displacement is not fitting in this, if it is not in the range of this range, then we should use a base relative addressing. If both program counter relative and base relative addressing are not helpful for us, then we should go for next format, that is format 4. Okay, so this extended instruction format is specified in the prefix plus added to the operation code in the in the source statement. So, sir, how to identify? I have to assemble or convert or translate the instruction by using instruction format number 4. So just you observe your program carefully. So if the opcode, that is opcode column, is nothing but instructions. So those instructions, if they are prefixed with the plus symbol, then you should understand that it should be translated or assembled by using the instruction number 4. Yeah. Then mhm. Then who has to decide this uh, by writing a plus symbol? So this is the complete responsibility of programmer. Programmer has to decide. So I should evaluate, I should convert this instruction, I should assemble this instruction by using a format number 4. Okay. So here this is the program what yesterday I explained you, which is written for SIC XC. Then here the main difference between this program and earlier program is nothing but, so here we have used some very important facilities of SIC. Those facilities are nothing but some extra instructions which are called as register to register instructions. Okay, register to register instructions I have used in my SIC program in the place of register to memory instruction whenever it is possible for me. For example, in line number 150, this is changed from COMP0 to COMPRAS. In SIC machine program, it was COMP0, but here it is now COMPRA, comma, yes. Okay, so since it is R is there here, compare the registers A and S. Okay, so here similarly, line number 165. In your program, you can observe in line number 165, earlier it was a TIX max length, now it is changed to TIXR T. Okay, so the only difference is that TIX increments the value of X and it compares the new value of X with the memory. Okay, this is the memory. But TIXR will increment the value of X, but instead of comparing that new value of X with the memory, it compares that new value of X with the register. That register here simply I have taken it as a T, which is a general working register. Okay. In addition to these all facilities, immediate addressing mode is there, indirect addressing mode is there. These all addressing modes are used as much as possible, and these changes or advantages are available in SIC XC architecture to improve the execution speed of our program. Okay. So why, sir, how we can improve the execution speed of our program? Because register to register instructions are faster than register to memory instructions. Remember, okay? Register to register instructions are faster than register to memory instructions because the register to register instructions are very shorter. Okay, very short registers. For example, if you consider COMP, COMPR, and any other register to register instructions, they are just 2 bytes length. Okay, 2 bytes length, but the remaining register to memory instructions are 3 bytes, 4 bytes instruction. Okay, that is third instruction, format number 3 instruction, and format number 4 instruction. But register to register instructions will be usually in the format number 2. So these registers instructions are shorter and they do not require any other memory reference. Okay, because of that, fetching the operand value from a register is faster than fetching the operand value from the main memory. So getting the or taking the value of an operand from the register is faster than taking or fetching the value of that operand from a memory. Okay. Okay, then likewise, this when using immediate addressing, the operand is already present as a part of the instruction. See here, immediate addressing, wherever you observe in your program, which is prefixed with a hash symbol, that operand is already present in a program as a part of the instruction, and we no need to take that value of that operand from anywhere in the program. Anywhere in the program means from memory or from register. So no need to fetch it from memory also. No need to fetch it from a register also. Immediate addressing mode will directly give you the operand value there. Okay. So use of indirect addressing also usually avoid the need of another instruction, because as in line number 70 you can observe there. So indirect addressing is avoiding the need of any other instruction. Okay, so these are some facilities we have in SICXC. You may also notice some of these changes requiring addition of other instructions to the program. So the following, for example, changing COMP to COMPR on line number 150 is forcing us to add the clear instruction on line number 132. It means that clear will remove the content of any registers. So if we are using COMPR register to register instruction, there are some situations are there you have to make or you have to delete the content of registers. Okay, so after your work has been done, so because of that only we have used one more instruction here, that is clear instruction. This still results in an improvement in the execution speed. The clear is executed only once for each record. Okay, for each record, and the benefit of this COMPR are realized for every byte of this transferred, byte of the data transferred. So the larger main memory of SICXC means that we have sufficient room or space or memory to load and run many other programs at the same time. So it is not compulsory that at the time I have to load and run the single program. It is not like that. Since there is a large space, is there memory is increased because the memory of SICXC is 2 to the power 20 bytes, right? So since there is a lot of memory is there, still it is wasting. So because only a small portion of your memory is taken by the program, and the remaining space or main memory can be used to load and run the other programs parallelly. So this kind of sharing of a machine or machine's memory between program is called as multi-programming. Okay, so sharing of resources of a machine, the resources like the memory, so and sharing the memory and running the program at the same time, multiple number of programs at the same time is called as multi-programming. To take the advantage, full advantage of this capability, we must be able to load the programs into main memory whenever there is a room or space in the memory, rather than instead of specifying a fixed address. Instead of specifying a fixed address, like in SIC, I think you have assumed that our program will start in the address 1000. Okay, instead of fixing like this the address, so wherever the memory is available in that space, you can go and you can install the sorry, you can load the or store the program. Okay, so wherever the memory is available in that available or free memory, we can load the program. So this process is called as program relocation. This is very important point. Keep it in your mind because it is asked many times in your exam. Explain the program relocation concept. So in next classes, I explain this program relocation. Okay. So what is program relocation? First, you understand here. Of course, in SICXC, there is a increase in the memory, right? Because In SIC it was just 2 to the power 15 bytes, but in SIC it is a 2 to the power 20 bytes. Okay, so because of this extension or increased memory, so the to take this advantage of this extra memory, we must be able to load the programs into memory wherever there is a room. Instead of loading and running only single program at a time, we can load multiple number of programs, okay, at the same time, and we can execute them. So here, wherever the room or space or memory is available, in that space I will keep on or storing my instructions. Okay, specific instead of specifying a fixed address for that at the assembly time. And this process is called as program relocation. Remember, okay. Then we'll see some instruction formats and addressing modes, what we are going to use in our SICXC program here. Okay, in figure 6, next slide I am going to show you that figure 6, don't worry. So that the figure 6, sorry, already I have shown you that figure 6 yesterday. I explained that diagram. Now this program is little figure 6, that is a SICXC program. Okay, so this SICXC program here in figure 6, note that the start statement specifies the beginning program address of 0 instead of 1000. This time we are assuming that our program is loaded into the address 0 instead of 1000. Okay, so translation of this register to register instruction such as clear and COMPR presents no new problems. Okay, so here using these register to register instructions and any other special instructions, they will not give us any problem. The assembler must simply convert the mnemonic operation codes to machine language using OP tab and change each register mnemonics to its numeric equivalent. So here it means that, so if it is an instruction with the memory, you just translate or convert it into machine language equivalent. If there are some registers are there in your instruction, then you simply just write the register numbers by using the symbol table. So it means that earlier I already told you, in symbol table symbols will be there, registers will be there. If symbols are there, their addresses will be there. If registers are there, their equivalent numbers will be there. Register numbers are there, right? I already told you. So similarly, here if it is operation code is there along with the operand, then you search that operation code in the OP tab and you get the address of that operation code. This translation is done during the pass 2, because yesterday only clearly I told you in during pass 1 we just define the symbol, but in pass 2 we do actual translation. Okay, at the same point at which the other types of instructions are also assembled. The conversion of register mnemonics to numbers can be done with a separate table. However, for this purpose it is convenient to use the sim tab. See, just now I told you. So in the sim tab, not only symbols and addresses are stored, we can insert registers and their numbers also. Okay, and to do this, symbol table should be preloaded with the register names like A, X, etc., and their values will be 0, 1, okay, 0, 1, 4, 8, 9, like this. Whatever the register numbers are there, those numbers will be also stored in this symbol table. Okay, next come to this page number 60 in your textbook. If it is not clear in my slide, you can refer your textbook there, no problem. You open page number 60, there you will get one SICXC program, same program once again. So here we have added object code column and location column here. So comment lines are removed here and location column is added and object code is also added like our SIC earlier program. So if you observe carefully location column, so first executable statement was STL, no? So that STL is stored in the address 0. It means that my program is starting or loaded or stored in the address 0. Then since STL is a 3 byte length instruction plus 3 I have done, then it becomes 0003. Okay, so LDB is also 3 byte length. It means that all instructions, maximum number of times all instructions will be in format number 3 only. So for plus 3 I have done, then it becomes 6. But in line number 15, if you observe carefully, it is not a J sub, it is a plus J sub. Plus J sub means it is format number 4, which is a length of 4 bytes. So plus 4 I have done, so it becomes 0000A, 000A, then LDA plus 3. Okay, like this, plus 3 plus 2 plus 4. So based on these instructions you should do here. Okay, so when you come to this 00110, after that plus 3 you do here because of this JEQ. JEQ takes 3 bytes and 0013 it becomes. Then after 0013 plus J sub is there, plus 4 you have to add here, so then it becomes 0017. Then plus 3, then it becomes 001A. Okay, like plus 3 again because the end of file is there, LDA end of file, plus 3 plus 3 plus 3, and here plus 4 again. So it is 0026, but now it becomes 002A. Okay, and here also byte EOF 3 bytes. So plus 3 plus 3 plus 3 plus 3. So then here 4096 is nothing but it is a 1000. Its equivalent hexadecimal is 1000. So plus 1000, then it becomes 1036. 1036, and clear instruction is in format number 2. Okay, so format number 2. So plus 2 you do, then you get 1038. So again clear instruction is there, clear A, then plus 2, then it becomes 103A, then again clear is there, so plus 2, that is 103C. Then plus LDT, it means plus 4 you have to do, so it becomes 1040. Like this, every location column you will write on your own by looking into these opcode column. Okay, then last what is the address here? 1076 plus 1076 plus 1, because here output device hexadecimal code is 05, so it is reserving 1 byte of memory, so it takes 1 byte of memory, so plus 1 it becomes 1077. Remember, your program ends at a address 1077. So this location column you have written now. Okay, how to write it, I think you understood. Okay, then the main task is this one now, how to generate the object code of each and every instruction line by line. Okay, so then this is the main challenging task for us. Today we will generate these object codes, and in the next class we will see how to arrange them in a proper manner, proper structure to get a proper object program. Today just we will see how to how to generate these object codes. Okay, just a minute, I have one more file here. See, the first instruction is here, that is STL return address. STL you have to find out opcode, and you should fill these 6 bits here. Then NIX BPE. So N is 1, I is 1. It means that it is neither indirect addressing mode nor immediate addressing mode. It means there is no any @ symbol and there is no any hash symbol also. So both of them should be 1 1 only. Then X is 0, B is 0, but it is P is 1. It means that for first time our assembler gives a first priority to program counter relative addressing mode. Okay, so in that program counter relative addressing mode, the calculation of displacement will be like this. Displacement is equal to target address minus the content of the register PC. Okay, so here target address is what here it is 0030. How it is 0030? You just find out the address of return address. Okay, you find out the address of return address in your program. Okay, you find out that address of return address in your program, it is 0030. Then program counter relative addressing mode, it is correct. So it means that you should know what is the content of the register PC. The content of the register PC will be always the address of the next instruction to be executed. Now we are in this instruction STL return address. Okay, STL return address in the line number 10. So next immediate address, immediate instruction is what here in line number 12. It is LDB length. Okay, so this LDB is in the address what here 0003. So we have to subtract these two, that is 33 minus 3. In your hexadecimal uh, calculator, you can do this subtraction operation. Here I have done it manually also. You do it with your calculator, no problem. 0030 minus 0003. 0030 is a target address of return address, and 0003 is the address of the next instruction. Next instruction is LDB instruction. Okay, so PC always contains the address of the next instruction. So displacement will be this much 02D. Okay, 12 bits of displacement I have to fill here. So this is my object code 17202D. Clear how I am getting this object code for the first instruction. So okay, come to second instruction, LDB hash length. Since hash is there, immediate addressing mode. Okay, so because of that only n will be 0, I will be 1. And since these all instructions are using memory reference, we have to use either program counter relative addressing mode or base relative addressing mode. If there is a memory reference is not there, then apart from these two relative addressing mode, we can use any other relative addressing mode. So first you should find out opcode of LDB, then n is 0, I is 1, x is 0, b is 0, p is 1 again, and e is again 0. Okay, so then target address of length is 0033 minus 0006. Why sir 0006? It means address of the next instruction to be executed. The next instruction to be executed is plus j sub in my program. Its address is what? It is 0006. So after performing these subtractions, you will get your object code as a 69202D. Okay. Next instruction, third one. Third instruction is a plus j sub read record. So since it is a plus j sub, okay. So here, since it is a plus j sub, it means that you have to use format number 4. Because of that only, here instead of 12 bits of displacement, I have written 20 bits of address directly, address field. Okay. So first you just find out the JSub opcode, and n is also 1, I is also 1. It means it's not immediate, it is not indirect, it is not indexed also, it is not base relative also, it is not program counter also. So when we use this program, this format number 4, extended format number 4, extended format, no need to use program counter also and base relative also. Okay, because I don't want to calculate a displacement here directly, I can take a 20 bits of address here. So no need to calculate the base relative addressing mode displacement or program counter relative addressing displacement. E value will be 1 since it is format 4. Then 20 bits of address I have to find out. How to find out? You will just go to read record, RD record in definition portion or section of your program. You find out the address of read record and directly it is 1036. But 20 bits are available for me, so I written this 0 here. Okay. So then fourth instruction is LDA length. Find out the LDA opcode, which is 00. I have written here, and NIX BPE you should fix the bits here. So n is 1, I is also 1, then x is 0, b is also 0, p is 1, e is 0. Okay. So address of length is 0033, and address of the next instruction to be executed is a CONP, which is stored in the address 000D. Okay, so because of that only program counter register, that is PC register content, will be 000D. When you subtract these two, you will get a displacement. That displacement is 026. Okay, so this is how we get the object code. So if you are doing right now practicing, then it is fine. Otherwise, in your free time after this class, by today evening, you should find out all the opcodes, object codes of each and every instruction of your program. Then you should send me that results. Okay, object codes, whether you are getting correct or not, you can cross check there only in your textbook. Okay. Don't make any mistakes. COMP has your immediate addressing mode. Find out the code of COMP and NIXBP bits you have to write here 0, 1, 1, I equal to 1, because it is a immediate addressing mode. Then X is 0, B is 0, P is also 0. Since no need to calculate a displacement, and because directly they have given here, if you observe this operand, directly they have given the value of operand as a 0. So directly I can take this as a 0 as a displacement here. No need to calculate a displacement separately. So then it becomes 290000. Okay. Then next is a JEQ end file. JEQ end file. It is a object code, opcode of JEQ you should find out. And N and I are 1, X is 0, B is 0, P is 1, E is 0. So our address of end file is 001A, and address of the next instruction to be executed is 0013. Next instruction is JSub, plus JSub is present in the address 0013. So when you subtract this one, you will get this answer, that is 007. Okay, like this you should find out the next instruction as a plus JSub, which is a format number 4. 20 bits of address, you will directly take it as 105D. It means it is address of read record, WRREC. Okay, so B is also 0, B is also 0, but E is 1. Then JC loop. In JC loop also you should use it, you should assemble it, you should solve it by using program counter native addressing mode only. Okay. Then LDA UOF. Here also program counter native addressing mode you should use. Okay. Then next one is STA buffer. So here also you should use the program counter relative addressing mode. The address of buffer is 0036, and address of next instruction is 0020. If you subtract it, you will get 016. Okay, N is 1, I is 1, B is 0, P is 1, P is 0. Then next is LDA 3. Since directly they have given the value here, directly you can take that value as a displacement here. Okay, 003. Okay, since the direct value you are taking, no need to calculate the displacement. So you are not using any relative addressing mode here. BRP. STA length. Here also program counter relative addressing mode you are using. Plus JSub. Again, fourth instruction, that is opcode of JSub. Then NI is 1, X is 0, B is 0, P is 0, but E is 1 here. The address of read record is write record is 105D. Then J at the rate return address. Here you can see J opcode you should write here, and N is 1, I is 0, X is 0, B is 0, P is 1, E is 0. Then if you subtract this, you will get the object code as a 3E2003 because displacement you will get it as a 003. Then C end of file. So how to do this one end of file? Already I told you in the SIC also. You go to appendix B, there you will search so hexadecimal code of EOF, that is 45, 4F and 46. Okay. Then clear X. Since it is a format number 2, clear opcode you write it as a B4 and X register number is 1 and there is no any second register, that is R2 register. So directly just put it as a 0. Similarly clear A opcode is a B4 and the name number of register A is 0. Okay, register 0. Then there is no any second register R2, so you keep it as a 0. Similarly clear S, opcode of clear is B4, S register number is 4, there is no any R2 register here, just keep it as a 0. Okay. Now LDT 4096. You can observe here there is a combination of both format number 4 and immediate addressing, right? So even though there is immediate addressing is there, no need to calculate the displacement. You just put the n as 0 and I as 1 and B also 0, P also 0, and again directly you take it as a 1000. Why 1000? The equivalent value of 4096 in hexadecimal is a 1000. So I have written it as 1000 here directly. And here I have prefixed it with on 0 because here 20 bits of auto speed you have to fill here. I have not written anything here, but you should write here. Okay, these all bits, zeros and ones, you should fill in this box. Okay, so object code will become 75101000. Next TD input. It's also same. Use program counter relative addressing mode here. Then JEQR loop. Here also it is the same. You use a program counter relative addressing mode. So here you may get some difficulty because sometimes you may get negative values there. Because here only you observe it is 1040. What is this? 1040? It is address of R loop. Okay, its address is 1040. But the content of the register PC is 1046. It means next instruction to be executed after JEQ is RD, whose address is 1046. So you can see here you will get a negative value here. Okay, so whenever you get a negative value here, you have to be very careful. You will get somewhat the value like FFA or something else. Okay, so be very careful. You subtract it with your hexadecimal calculator, then you will get it correctly. Read record. Read from input device. Again, it is also program counter relative addressing mode. You use it and you get the object code as a DB2013. Similarly, COMPR A comma yes. COMPR register to register instruction. So format number 2 it is. So COMPR opcode is a A0 and A register accumulator register number is 0. S is a general working register, its number is a 4. Similarly, JEQ exit. Here also you use a program counter relative addressing mode only. Here 25th instruction is very interesting. STCH buffer comma X. So STCH opcode you will find out here, and N and I will be 1 X will be also 1 here because of this comma X modifier. Okay, in your instruction the operand contains the modifier comma X, then small letter X flag bit will be 1, and again you use the same program counter relative addressing mode and evaluate the displacement. sorry, since I have written here, it is wrong method. This is the right method. Since you are using the indexed addressing mode, okay, so no need to use this p here, because if you use a program counter also, uh, because of that range whatever I had told you, so that range, the displacement will not fit in that range. Because of that only, then I start to use base relative addressing mode. Remember, base relative addressing mode, and I put this p value as a 0. Okay, then if you are using base relative addressing mode, then your displacement formula will be like this: displacement is equal to target address minus the content of a register B, and the target address is nothing but here it is the address of buffer. Okay, you search the address of buffer as 0036 minus the address of the the content of the register B is 0033. If you go and observe LDB instruction and base assembler directory in your program, their programmer is telling to assembler to put the value 0033 into the register B. Okay, so register B content is 0033, then you will get the displacement as a 003. Here I have written right side, it is a base relative addressing mode. Refer page number 62 in the textbook. I will explain you in the next slide only, it is there. Okay. TIXRT format number 2 it is, and here JLT loop. So here also B is 0, P is 1. Okay, no any problem here. Next STX length, here also you should use base relative addressing mode instead of program counter relative addressing mode, because here I have written it is base relative. If we calculate a displacement with the program counter, displacement will not fit in 12 bits. That is, displacement is out of the range of minus 2048 to plus 2047. Because of that only I leave this program counter addressing mode, then I go to base relative addressing mode. Okay, then R sub instruction by using the format number 3, but since there is no any memory reference here, I don't use base relative also, I don't use program counter also. Directly I write the address as a 0000. Then X F1. Okay, F1 only, F1 is there, so F1 hexadecimal constant directly. And clear X format number 2. LDT length format number 3 by using program counter, base relative. Here also the range of displacement will not fit in this range, so I go with the base relative addressing mode. Okay, TD output, okay, format number 3, JEQW loop. So here also program counter relative addressing mode, LDCH buffer comma X. Okay, so here you should not use again program counter, you should use a base relative addressing mode. Then WD output, here also you should use a third format, but by using a program counter relative addressing. TIXRT format number 2 it is. The register number for T is 5, and here there is no register, so I kept it as 0. And here JLPW loop, it is also in format number 3 with the program counter relative addressing mode. Then last is a R sub, again it is a format number 3, so it becomes 4F0000. X05, that is 05 directly. So these all are the instructions, how we have converted them into object code, how we found the object code of each and every instruction in our program. Then within 2 minutes this meeting will end, and in next class I explain you how to write this object program for these all object codes. Okay, you know already header record, text record, and end record. Again we use those records. In addition to these 3 records, we use one more record here. After text record, I use one more record called modification record. Modification record, why we should use, because I told you today one concept, that is program relocation. At the same time, since the memory is large, at the same time I can upload and run multiple number of programs in the same time in the machine, wherever the memory is available, wherever the room is available for me. Instead of running only single program at a time, I can run multiple number of programs. So that concept we will use here. Because of that only modification record I have to use in my object program, that I will explain you in next class. Okay. Now you can do the meeting.